Good morning to all. Is this audible? You can type in the chat box also. Yes, Pawan Chandra. Is the screen visible? Okay. Thank you, Pawan. We'll go for the next topic in unit number 4. So what we had seen in last class, that I'll give you a small glance of it, because this topic is a continuation of that topic which we had solved. So we had seen this block coding principle. This block coding principle consists of a channel encoder where messages of k bits are given as input, and in the encoding part these message bits are being added with 10 check bits with n minus k, and the total information which we get at the output of your channel encoder is n bits. So this is your block coding principle. So this block coding principles will have codes n comma k, and there are two different formats for representing the block codes. One is systematic and a non-systematic. So we have seen in systematic that message will appear first, then check bits will appear, whereas in non-systematic, message and check bits will be mixed up in the same block. So it will be very difficult to identify which is message bits, which is check bits. So that we call as non-systematic. So now we had seen a type of the block codes as linear. So what does this linear property state? That if sum of two code vectors produces another code vector, so then it can be called as a linear codes. And if the linear codes are being implemented in block codes, we call it as linear block codes. So these are the representations. X is represented by M and C, message number of message bits, and the number of check bits, MC. And what is this mean? M is, M represents your messages of k bits, whereas C represents the check bits representing Q. So altogether we can find X is equal to mg. G is your generator matrix of size k cross n. And in terms of matrices, we can find X as X is equal to m over G. Okay, X in 1 cross n, m 1 cross k, G k cross n. So this is the size of that. Then we had solved a problem as how to find this generator matrix G, how to find code vectors C, and all. So this was an example for that. Determining the code vectors when a generator matrix G is given. Okay. Now in today's class, I think hope all had joined. Let me check it. Then I'll start. Okay, so around 12 people. Okay, no issues. We'll start. So in today's class, we'll be seeing about the parity check matrix H. In the previous class, we had found generator matrix. You can see in the problem, the generator matrix was given, and they determined P submatrix. They determined check bits C is equal to MP, and they had found code vectors for every message bit. So we have done this easily. So next topic lies in parity check matrix. So what is this parity check matrix is? So for every block code, there is a parity check, which is represented as H. For every block code, there is a parity check matrix H of the size Q cross N. So Q is your N minus K. So how do you find this parity check matrix is H is equal to P transpose is to IQ. So I is your identity matrix. So the whole represented as Q cross N. So what is this P transpose? How do we obtain this P transpose is that we have a P submatrix. From the given question or from the obtained generator matrix, we have P submatrix. So write that P submatrix. So for example, if we have a K cross K cross Q, we have K cross Q P submatrix. So I'll write it. So P11, P12, P13 till P1Q, P21, P22, P23, P24 till P2Q, P31, P32, P33, P34, P35, P35 till P3Q, and next P41, P42, P43 till P4Q, and this column extends till Pk of the first column. This extends till the Pk of the second column. This extends till the Pk of third column till Pkq. So this is your P submatrix depending upon K and Q value. So how do you obtain this P transpose? Transpose is a simple concept that changing rows into columns. As you all are familiar in mathematical determinants and matrices. So P transpose is changing rows to columns. So whatever we have in the first row, write it as first column. Whatever we have in the second row, write it as in second column. Whatever we have in the third row, write it in the third column, and so on. So we get here the first row P11, P21, P31 till Pk1. In the second row, we have P12, P22, P32 till Pk2. The third row, we have P13, P23, P33 till Pk3. And at last, we have P1Q, P2Q, P3Q till Pkq. So this is how we can obtain parity check matrix. Equation number 3.3.13. Hope you all are familiar with the transpose of matrices. So at last, what is our requirement is? Our requirement is to determine H. So H is of the matrix Q cross N. So write it in P transpose is to I. So your identity. So write the same P matrix as it is. Then what is the identity matrix? Till Q. So till how many Qs we have? Write the identity matrix. So this will become your parity check matrix. Equation 3.3.14. If in a problem, if generator matrix is given, we can easily find a parity check matrix. If parity check matrix is given, we can easily find generator matrix, and vice versa. Whatever might be, we can do it vice versa, and we can find generator check matrix or parity check matrix, and using that we can find the code vectors easily depending upon the problem. We'll see that also, don't worry. So moving on to the next topic is the Hamming codes. We are following the same term Hamming codes from unit number 3 also, the same concept. Hamming codes are n comma k linear block codes that satisfies these following conditions. There are 4 conditions for every code that has to be satisfied. One is the number of check bits q which we are obtaining should be always greater than or equal to 3, and the block length should be 2q minus 1, 2 power q minus 1. Block length should be in this way. If you are having q is equal to 3, for example, with the least I tell you, for q is equal to 3, we will have 2 power 3 as 8, 8 minus 1 is equal to 7. So block length will be 7. And if the number of message bits should be always k is equal to n minus q. So k will be equal to n minus q, where n we had found it as 7 and the q we had found it as 3, so it will become k is equal to 4 if you take q is equal to 3. Then the n comma k linear block codes will become n is equal to 7, a is equal to 4. So 7 comma 4 linear block codes is your minimum Hamming codes. Minimum. Next, minimum distance required is always 3. So the minimum distance is calculated in the number of digits in which these two code vectors differ in. If you take two code vectors, the minimum distance should be separated is 3, which we call as d minimum. So next is to find code rate for this Hamming codes. Code rate, as you all are familiar, r is equal to k by n. Now substitute this k value, whichever we had got it, n minus q divided by n. From this recall and substitute, so we'll get 1 minus q by n. Now substitute the value of n. So n is here, 2q minus 1, so 2q minus 1. Okay, so r will become 1 minus q divided by 2q minus 1, or you can simply write r is equal to k by n also. So from this equation we can approximate that if q is very much greater than 1, you can see that if q is very much greater than 1, we will get r is approximately equal to 1. So this shows that we will get 100% of efficiency approximately. So this is the reason why we concentrate on Hamming codes. Okay, this is the reason why we concentrate on Hamming codes, since it gives an approximation 100% of efficiency. So r is your code rate or the efficiency. R is equal to, will be approximately equal to 1. After the Hamming codes, definition and obtaining the value of r, we'll be seeing error detection and correction capabilities. How much amount of error can be found out and how much can be corrected. I think we had seen this in our unit number 3 also. Since the minimum distance of Hamming code is 3, the minimum is 3, it can detect up to 2 errors and correct 1 error. It can detect two errors and can correct one error. So this is what return is. So for detecting double errors, d minimum greater than or equal to 2 plus 1, that is d minimum is greater than or equal to 3, and correcting up to one errors, d minimum greater than or equal to 2t. We are saying 2t plus 1, which is 2 of 1 plus 1, which is d minimum greater than or equal to 3. So which satisfies this. Okay, error detection correcting capabilities of Hamming codes. So next we'll be seeing a problem on the error detection, error correction, determining code vectors and generator matrix for the linear block codes. So the question is, the parity check matrix of a n comma k linear block code is given by some matrix H. Some matrix H is given. So what is the n comma k? N comma k is n is 7, k is 4. So it is given as it is 7 comma 4 linear block code is given by H is equal to, in the first row I'll read it out, 1 1 1 0 1 0 0 1 1, second row 1 1 0 1 0 1 0, third row 1 0 1 1 0 0 1. So this is your given H matrix. So from this H matrix we should determine the generator matrix G, code vectors, all the code vectors. We need to determine the minimum distance between code vectors. We need to find how many errors can be detected and how many errors can be corrected. So this is our question. So now to solve this, first we should be familiar with the H matrix. What is H matrix? I will show you back. So H is what? H is P transpose IQ. P is your transpose of the P submatrix and I is the identity matrix. So first let us determine this Q and N. Then it will be easier for you. Okay, in order to determine Q, what do we require is N and K. So from this given question, find N. N is 7, K is 4. So then the number of check bits will be always Q is equal to N minus K. So you get Q is equal to 3. So from this we can find how many identity matrix is there. Identity matrix is I, Q. So Q is 3. So I3. So this last 3 are your identity matrix. The last 3, 1, 0, 0. I'm showing in equation 3.18. This 3, these 3, these 3 are your identity matrix. So which I had separated by a blue dot. In the question it will not be given. Not to segregate and show you, I am differentiating the question itself as a blue dot in between the columns from P transpose and IQ identity matrix. So this is your identity matrix. So now next let us find the P submatrix first. So we know that the P submatrix is having a size Q cross N, so which is 3 cross 7. 3 Q is equal to 3, N is equal to 7. Okay, so we can write the H submatrix as H of 3 cross N, just Q cross N. So 3 cross 7. So we get the matrix as P transpose. This is your P transpose, P11, P22, so P21, P31, P41, P12, P22, P32, P42, P13, P23, P33, P43. And the remaining is identity matrix 1 0 0 0 1 0 0 0 1. Now first find the write the P transpose whatever is given. So whatever is given from the question, we can find that P transpose is this: P11, P21, P31, P41, P12, P22, P32, P42, P13, P23, P33, P43. So the given is your transpose matrix. Write it as it is in the question. So 1110, 1101, 1011. From the P transpose, find P. How do we remove transpose? Is that convert your columns into rows. That's all. Or rows into columns. So I am replacing all the rows into columns. This row as this column, this row as this column, this row as this column. I write it. So I'll get the P matrix P 4 cross 3. This is your P submatrix. So any doubts till this? Till this equation 3.3.18b. If you have, you can type in chat box. I'll also check it. Then the remaining is same. After getting P transpose, how to get G, I'll tell you also. Let me check in chat box. Hello. சொல்லுங்க இல்லைங்க டிவே முடிய போகுது. ஓகே. How do we get elements in matrix? You're asking for P matrix? You're asking for P, is it? I'll type it. Is it for P submatrix? The question you're asking for P submatrix. Or P transpose. Okay, okay. I'll show you. Just a minute, I'll show you. The P transpose is obtained from our given question. So I'll show you that. See that the parity check matrix of a particular 7,4 linear block code is given by this H. So what is our H? H is 1, 1, 1, 0, 1, 0, 0. This is the identity matrix which I had wrote in blue color. After the blue color dots, everything is in identity matrix. So in the second row, 1, 1, 0, 1, 1, 0, 1, 1. Okay, so this is your P transpose. This is your P transpose. Why? Because our H is P transpose identity. Okay, you can see that. Make a note. The first row is 1110. Second row is 1101. Third row is 1011. Okay. First row, let me check. First row is what? P transpose 1110. Second row 1101. Third row 1011. Same the question. Is it same? 1110, 1101, 1011. 1110, 1101, 1011. This is how to find P transpose. It is from the given question itself. Okay, any other questions? After finding the P transpose, we need to find P submatrix. how do we find P submatrix is that converting the rows and columns, rows into columns or columns into rows of the P transpose, we get P submatrix. If we do that, we'll get P submatrix. Then after P submatrix, we'll be finding G, your generator matrix. Shall we proceed? If we are able to understand what is H, how to find N, how to find K, how to find Q, if Q is determined, the remaining all is your P transpose. From the question itself, directly we can write P transpose also. If you are determined Q easily. When do we get Q easily? Is that if we find N value and K value. If N value and K value is known easily, we can find Q value. With the Q value, we can find identity matrix. If identity matrix is known, the remaining all is your P transpose. So from the P transpose, we can determine P submatrix easily. Okay. Next, going to the slide, we need to find generator matrix. Why? Because our question is to determine that. Find the generator matrix is the question. Okay, so we'll go for that. So the generator matrix formula is, the representation is G is equal to IK is to PK cross Q. PK cross Q over K cross N. Okay. The simple thing is that we need to substitute only the values of K, Q, and N. We'll get it. We substitute the values of K, Q, and N. Easily we can write the matrix representation. So what is that? Is that K is 4, Q is 3. We have determined N is equal to 7. So simply this G will become identity I4 is to P 4 cross 3 over 4 cross 7 matrix. I'll show you this formula, generator matrix G. This is our generator matrix in the previous problem that we had done. G is equal to IK identity matrix over P sub matrix. G is equal to IK is to P K cross Q. Okay. This formula we are going to take. Substitute K is equal to 4, Q is equal to 3, N is equal to 7. Simply easily we'll get G matrix, generator matrix. So then what is this IK? I is always your identity matrix. IK is always identity matrix. So I4. So write identity matrix in 4 cross 4. Identity matrix 4 cross 4 is 1 0 0 0 1 0 0 0 0 1 0 0 0 0 1. Then put a semicolon in order to differentiate that this is identity matrix and this is parity submatrix, P matrix. So parity submatrix is obtained from your P transpose. So which is 4 cross 3. 4 cross 3. So then write as it is. 111 110 101 011. So bring this P submatrix as it is, which is equation 3.3.19. So this altogether constitutes your required generator matrix of the size 4 cross n. Let me see for any queries or doubts, because the remaining is what we had done in the previous problem. From that we'll be finding code vectors. I'll check for any queries or questions for this determining generator matrix. Then we'll proceed. So any questions? Okay, I think I can proceed since there are no questions in the chat box. No. Okay, now we had found generator matrix G. So next is to determine all the code vectors. Second is list all the code vectors. So we'll list it. Don't worry. For finding all the code vectors, we need to recall the formula. C is equal to MP. MP. So what is the M? M is your number of messages. How many messages we have? We have K is equal to 4. So we'll be having 4 messages. So which is M1, M2, M3, M4. And P we can obtain from the G, which is this. So P is 4 cross 3. So you can write as it is. So now we will be having a question. How many check bits will be there? So how many check bits will be there is that check bits will depend upon Q. Okay. So Q is somewhere. Okay. Q is 3. So we'll get C1, C2, C3. So this is how to find code words. C1, C2, C3. Since Q is equal to 3, message M is M1, M2, M3, M4. Since message bits comes from K is equal to 4, and parity matrix, sorry, not parity submatrix comes from 4 cross 3. So write it everything. C1, C2, C3, M1, M2, M3, M4, and the parity matrix 4 cross 3. So you have 4 columns, sorry, 4 rows and 3 columns. 4 cross 3. So next method is easier. How to find C1, C2, C3. C1, C2, C3 can be easily found out by just multiplying M1, M2, M3, M4 with the first column. Multiply this row with the first column for finding C1. For finding C2, multiply this first row with the second column. For finding C3, multiply this row with the third column. So we will get it easily. Yes, sir. So we'll get 1 into M1 modulo 2 addition, 1 into M2 modulo 2 addition, 1 into M3 modulo addition, 0 into M4. Similarly for C2, 1 into M1 modulo addition, 1 into M2 modulo addition, 0 into M3 modulo addition, 1 into M4. C3, 1 into M1 modulo addition, 0 into M2 modulo addition, 1 into M3 modulo addition, 1 into M4. So in each of the C1, C2, C3, 0 is present. So 0 into anything will be 0. So remaining will be getting C1 as M1 modulo 2 addition, M2 modulo 2 addition, M3. C2 as M1 modulo 2 addition, M2 modulo 2 addition, M4. C3 M1 modulo 2 addition, M3 modulo 2 addition, M4. So this equation 3.320 will generate code vectors. Will generate code vectors. Now, for example, I'll do it for one thing. I'll do for one example 1011. If I substitute M1, M2, M3, M4 as 1011, what do we get as C1, C2, C3? Is that substitute it here. What is C1? C1 is M1, M2, M3. So M1, M2, M3. So do modulo addition of that. We get 0. For C2, M1, M2, M4. Take M1, M2, M4, which is 1, 0, 1 again. When you perform modulo 2 addition, we get 0. For we get 0. For C3, it is M1, M3, M4. M1 is 1, M3 is 1, M4 is 1. Do modulo 2 addition, we get 1. So for message vector 1011, check bits are 001. 001. So we can write the code vector as M1, M2, M3, M4, C1, C2, C3. So M1, M2, M3, M4 is 1011 is to, this is used to differentiate. Then C1, C2, C3 is 001. So using the same procedure, I have tabulated, so you can check that for the remaining messages also. So we have message M1, M2, M3, M4. Check bits we get C1, C2, C3, C4. Code vector or code word is combination of M1, M2, M3, M4, C1, C2, C3. So we can find code vector or code word. Similarly for all the messages. Why we are finding for all the messages that in the given question, it is set to find for all code vectors. So our message bits are 4. So 2 power 4, what we get is 16. So right from 4 zeros, 0, 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 1, 0, 1, 0, 0, 0, 1, 0, 1, 0, 1, 1, 0, 0, 1, 1, 1, 1, 0, 0, 0, 1, 0, 0, 0, 1, 1, 0, 1, 0, 1, 0, 1, 1, 1, 1, 0, 0, 1, 1, 0, 1, 1, 1, 1, 0, 1, 1, 1, 1. So we get 16 different messages. For all these 16 different messages, we need to find check bits C1, C2, C3 appropriately and write code vector as in this table. So you can check this table and at last how to find weight of the vector I'll tell you. Just check this table. Message bit M, check bits C, code vector or code word. If you do modulo 2 addition correctly, you will get this check bits easily. And if check bits are obtained, message bit with check bit gives you code vector or code word. I'll give you some I'll give you some 3 or 4 minutes. Kindly check this table. Then I'll say you the how to find weight of the code vector. Check this table whether you're getting this C1, C2, C3 correctly. Some 3 or 4 minutes I'll give you time. Then I'll check in the chat box for any queries. Then I'll proceed for the next. Why? Because without understanding this concept, we cannot go for error detection and correction. Yeah, question is how to write check bits. Okay. How to obtain K value. First, let me tell you how this linear block code is being written. Okay. So linear block code is written as n comma k. See here with encoder diagram, k bits and n bits. So this n bits consists of k as well as n minus k. So this n minus k is your check bits. I think this check bits can be obtained by n minus k. Okay, which is your q value. Q is equal to n minus k. Okay, and how do we write this linear block codes? Is that n comma k block codes. N comma k block codes. Now see the question. For this question, tell me what is n, what is k value. For this question, here the question is given as the generator matrix for a 6 comma 3. 6 comma 3 represents n is 6, k is 3. That only we had solved. N is 6, k is 3. So how to find check bits? Q is n minus k. So n is 6, 6 minus 3, you get q is equal to 3. Similarly, in this problem, in our problem, we are having parity check matrix of 7 comma 4. 7 comma 4. So it is in the form of n comma k. So n will be 7, k is 4. From this we can find q. So q is n minus k. So see here, number of check bits can be obtained from n minus k. So n is 7 minus 4, which is your k, that is equal to q, which is 3. So q is equal to n minus k, which is 3. So any doubts now? Venkat Sivasai and Nagasai Lakshmi, Srikala. Now I'll type you an n comma k code. N comma k code. Find n and k. What is n? What is, okay, n is 15. Okay, what is, okay, 15 is correct. K, you can write n is equal to 15. K is 6. Then I'll ask you, determine check bits. Check bits are, determine the check bits. It indicates q is equal to n minus k, which is n is 15 minus our k value is 6. So we get 9. So 9 is your check bits. So this is how to determine check bits. This is how to find k value. So any doubts now for Srikala and Venkat Sivasai? We can find the q and k by matrix also. Yeah, sure. Yes, we can find by using that also. Okay, thank you. We can use this method also, Tanuja, as you said. K and q is being given by the matrix. Using the formula q is equal to n minus k, we can find it easily. This should be n, Tanuja, k and n by the matrix. Okay. By that also we can find. Yeah, okay. So shall we proceed? So for the given question, we had found generator matrix, we had found all the code vectors. Since we are having message bits as 4, so 2 power 4 we got 16 code vectors. So we will be getting 16 messages. For that 16 messages, each and every message will have individual code vector that we are found in this table. So after finding the code vector or code word, we need to find weight of the code. How much weight that this particular serial number of message, serial number 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, any of this has. So how to find the weight of the code vector is, I think already we had seen, so no problem. Today also I'll explain. See the code vectors. Just concentrate on the code vectors with combination of M1 and C1, M1, M2, M3, M4, C1, C2, C3. So see this for the serial number 1. See how many number of ones are present. There are no ones. So here we'll keep it as 0. So the concept is that the presence of non-zero elements should be counted. So that will give the weight of the code vector. Since we are dealing with binaries, we have only two representations, zeros and ones. So just count, for your easier method, count the number of ones being present. Here in the second serial number we have in this 3, so 3 is the weight. So in the next we have 3, so 3. So in the next we have 4, so 4 number of ones, so 4. Count the number of non-zero elements. This is the procedure. If you count the number of non-zero elements in that code vector, so that will give the weight of the code vector W of X. So for this it is 3, for this it is 4, for this it is 4, 3, 4, and it goes on. At the last you can see that for serial number 16, the code vector is all are ones. Everything is 1. So the weight of the code will be 7. For this specific problem, so if messages vary, check bits will vary, and the code vector also will vary. So depending upon that, we can find the weight of each and every code vector. So this is how to determine weight of code vectors. You can check this also. Do not consider the M and C separately. Together we wrote M and C together. It is X code vector or code word X. So that we need to see. So let me check for any questions in this weight of the code vector in the chat box. My code vector is I'm giving a question in the chat box. I'm giving a code vector. My code vector is 110110. Find the weight of the code. So how did we find is that the number of non-zero elements. So there are 5 non-zero elements in this code vector 110110. So we get 5 is the weight of the code. understood how do we find for each and every code vector or code word. So now let us go to the next step, that is to determine minimum distance. Our third question is to determine minimum distance between code vectors. So how do we find the minimum distance between the code vectors is that the smallest weight of any non-zero code vector is 3. You can see from the table itself. From the table itself, we can see that there will be 16 code vectors. In that, the smallest weight of any non-zero code vector is 3. You can see here. See here, leave the first one since we don't have any weights. Okay, you can see that the weight of the code. What is the minimum weight of the code in this weight of the code table? It is minimum 3 for all the non-zeros. Okay, you need to neglect in this 0. Why we are neglecting 0 is that in messages M1, M2, M3, M4, we don't have any message at all to be transmitted. So we cannot find it as we cannot find a distance for that, which is having 0 information. So we are neglecting this first serial number. So remaining all you check it for weight of the serial number 2, 3, 4, 5, 6 and all till 16. What is the minimum weight of the code? So the minimum weight of the code is 3. So we can write the minimum distance of the linear block code is equal to the minimum weight of any non-zero code vector. Minimum distance is 3. So this is why I had determined the weight of the code also. So from this we can see, apart from the non-zero code vector, so this is your non-zero code vector. Apart from that, we get the minimum distance is 3. So the smallest weight of any non-zero code vector is 3. So this is how do we find minimum distance between code vectors. So now the fourth one is determining the error detection. How much errors it can detect and how many corrections can be done. So we know the formula, d minimum is equal to 3. So it is your minimum distance greater than or equal to s plus 1. So d minimum is known, which is 3. So 3 greater than or equal to s plus 1. So take this one that side. So 3 minus 1 will be 2. So on rearranging, we'll get s less than or equal to 2. So this is your detection principle. S less than or equal to 2. Okay. So this problem will detect 2 errors. So but how many errors it will solve will depend upon the formula. D minimum greater than or equal to 2t plus 1. So D minimum is 3 greater than or equal to 2t plus 1. Take this one that side. 3 minus 1 will be 2. So 2 greater than or equal to 2t. So t on rearranging will become t less than or equal to 1. So this problem will correct only one error. So always if any Hamming code or Hamming distance has minimum Hamming distance of 3, it will detect two errors and correct one error. Detecting two errors, correcting one error. So this is your property also, which is being satisfied. So any doubts in this problem? Because almost it took 1 hour for this problem to be solved. Let me check for in chat box. I'll keep this slide for 2 or 3 minutes. If you have any doubts, you can ask in the chat box. Always the Hamming distance, minimum Hamming distance. If it is 3, then always by the property of Hamming codes, we can detect two errors and it can correct only one error. Yeah, whatever problem you take, the minimum Hamming distance will be always 3. That is the property of Hamming codes. If you check any problem, the Hamming distance of minimum will be always 3 only. You can check it also. If you solve in future problems also, you will get minimum Hamming distance as 3. So then we'll be detecting up to 2 errors and correcting up to 1 error. So which is a property of Hamming code itself. Okay, so we'll go for the next topic. Okay. Next is 7,4 encoder. How to draw this 7,4 encoder? Okay. So this is a diagrammatic representation which encodes n is equal to 7 and k is equal to 4. How to draw this? It's what you are going to see in this diagram. So from this we can find k values, right? K number of bits can be found out. How do we find? K is 4 since n comma k. So n is 7, k is 4. So k represents your message bits. So message bits M1, M2, M3, M4. So this represents your message register, which stores your number of message bits. So then from this Hamming code itself we can find Q easily, which is the number of check bits. So the number of check bits Q is n minus k. So 7 minus 4. So we get 3. So C1, C2, C3. C1, C2, C3. So which we called as check bit registers. C1, C2, C3 check bit registers. Always we should start writing from the LSB. So MSB is your lowest and MSB is your highest. Always write in this format. Okay. So the interconnection between this message and register and the check bits can be obtained by doing a simple modulo 2 addition, which you all are familiar, which is your XOR exclusive or operation or your XOR operation. Okay, exclusive or XOR operation. And this are being connected, C1, C2, C3 are being connected depending upon the problems. Depending upon problems, we get C1, C2, C3. So what is C1? Let us check. Let us check in the previous problem. C1 is obtained due to 3. One is M1, M2, M3. So let us check that for this C1. It's for a small example, we'll see that for this C1. See here, in this question, C1 is obtained due to M1 model 2 addition, M2 model 2 addition, M3. So let us check in the diagram. Let us check. C1 is obtained due to model 2 addition of this line, which is from M1, this line, which is from M2, and this line, which is from M3. So M1, M2, M3 gives C1. Model 2 addition of M1, M2, M3 gives C1. Similarly for C2 we will see. So for C2 it comes from M1, M2, M4. Let us see that also. For C2 this M1, M2, M4. Let us check the diagram. For C2C, where it comes from? Comes from M1, it is from M2 and M4. So the modular addition of M1, M2, M4 gives C2. Similarly, you can find it for C3. For C3, it is obtained from M1, M3, M4. So M1, M3, M4. Let us check for C3 bit. M1, M3, M4. C3 is obtained by modular 2 addition of M1, M3, M4. M1, M3, M4. So this is how to draw this encoded diagram for 7,4 Hamming codes for the above problem, what we had seen. We have seen this problem, right? I'm taking the same problem as an example. This I'm drawing C1, C2, C3. And it will differ depending upon the problems. It will be different as obtaining C1, C2, C3 depending upon each and every problem. So then we give an input bit sequence, then we need to obtain an output bit sequence. So we have a switch in between that. Okay, a switch is connected. So that's all. So this is your encoder of an Hamming code. This is how to draw encoder. So any doubts in drawing encoder? Let me check that box. Any doubts in encoder? Any doubts or queries? Because if encoder part is over, next is we need to decode the sequences. So for decoding, we have a different procedure. How to decode each and every code vector. By using a simple technique is there, so that is different. So if you have any doubts, you can ask till the slides. இந்த வாரம் ஃபுல்லாக ஒரு நாள் எக்ஸாம் ஒரு நாள் கிளாஸ் நாளைக்கு ஷெட்யூல் எல்லாருக்கும் காமன் ஆமாம் உங்களுக்கு எப்படி அடுத்த டேட்டா கம்யூனிகேஷன் கிளாஸ் அடுத்த மொபைல் கம்யூனிகேஷன் So after the encoder of Hamming codes, we have decoder. So in decoding, we'll be using syndrome decoding to correct errors in linear block codes. So for that, we require H, which is your parity check matrix. So H is obtained by P transpose IQ over Q cross answer that we require. Then we need to see an important property that the decoding is done without any errors. The first is that if let X be your code vector and Y be your received vector, if X and Y are same, or if Y is equal to X, then there is no error. And if Y is not equal to X, there will be an error being created. So decoding without errors has to be done correctly. So for that we go for syndrome decoding. So this syndrome decoding will depend upon the H matrix that we had seen, which is your parity check matrix. So which is obtained from the linear block codes. Okay, so take this H matrix, transpose that. It is simple. So as we had done earlier, PT with P. Now H with HT. So HT, which is your transpose matrix, will become P and I. So we'll see that in a problem how to do this easily. So P will become your submatrix of K cross Q and I will be your unity matrix always. So then the important property of this syndrome decoding is XH transpose is 0. X H transpose to be as 0. So X is your code vector. Okay, because you can see that transmitted code vector. So we need to find if it is 0, then we may get Y as without any errors. Okay, you can see that. You can write the H as H1 cross N, HT transpose N cross Q, which should be always 0, which will be true for all the code vectors. Okay, H transpose will be always 0 for all the code vectors. So this is your property. It is always true for all the code vectors. Okay, so let us take an example. I'll show you with an example. Consider a parity check matrix. HT is obtained like this. So this is your given question. Assume that this is your given question with matrix size 7 cross 3. So where 7 cross 3 represents your n is equal to 7, q is equal to 3. Okay, we are finding H matrix. Now I consider a code vector. I consider a code vector x is equal to 0, 0, 1, 0, 0, 1. So from the table you can take this. I'm taking a code vector from the table. So the H matrix from example of H, I'm taking H, I'm making transpose of that, and I am taking X, which I'm taking a third code vector. So I'm taking third code vector from the table. So I'm writing X and H transpose. So now what I'm going to do is that I'm going to perform X H transpose. So X is here, H transpose is here. So now do multiplication 0 into 1, multiply this row into the first column. Okay, and then multiply this row with the second column, multiply this row with the third column, and check whether you're getting everything as 0. You'll get it. So here 0 into 1 0, 0 into 1 0, 1 into 1 1, 0 into 0 0, 1 into 1 1, 1 into 0, 0 into 0 0, 1 into 0 0. So you'll be having for the first row, first column, first row, first column, we get 1 modulo 2 addition 1. So 1 modulo 2 addition 1 is always 0. Similarly, you can check it for others also using exclusive OR operation. So I will be getting X H transpose as always 0 0 0. So this is the important property for decoding, and this we call it as syndrome decoding. And how do we use this syndrome decoding in eliminating errors is that if you do Y H transpose, if you do Y, which is your received code vector, into H transpose, if everything is 0, then we say that Y is a valid code vector, means that there is no errors. And if Y H transpose is a non-zero element, is a non-zero element. If it is a non-zero element, it shows that there are some errors, and Y which is received, is an invalid code vector. Always if you do X H transpose, will be getting 0. Take any code vector, multiply with the H transpose, it will be always 0. Similarly, whatever we get at your receiver, you'll be having Y, which is a received code vector. So that you do with the corresponding H transpose and see if it is 0, then there is no error and it is valid. And if it is a non-zero, then there is an error and it is invalid code vector. So this is how to use syndrome decoding. And how do we check the error bits and correct them? Okay. So any doubts in this? We'll see with an example, the definition and the example. Do not worry. We'll see that in detail. Okay. In next class. So any doubts in this? If Y H transpose is 0, that means X and Y are same. There will be no error. Y will be valid. And if Y H transpose is a non-zero, then it shows that there is some error in that corresponding bits. Wherever we get that non-zero element, that bit is an error, or that sequence of received information is an error. So then we can rectify it either by retransmission or by checking. Okay, so let me check for chat box for any errors. Yeah, in the problem we have taken X matrix as third column. Okay, you take any other vector also. We can take any other code word or code vector and do. If we take any other code word or code vector, then we need to perform H transpose. If we perform XH transpose, we will get 0 only. Check it. Take any other from the code vector. Do XH transpose. Check. Surely you will get 0 only for all the values. For all the check bits, you will get 0 only. So refer that. Yeah, you will get surely for all the 16 serial number 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. You check with the corresponding H transpose. Obviously, you will get 0. No, you can check later also. No issues. You can check for each and everything, you will get 0 only. Because this is at your transmitter. Whatever we transmit, will be transmitting without errors only, no. Whatever the message that we give is always without error. When do we get error? We'll be getting error only. Yeah, we will get error only after the encoding and after the signal is being transmitted through the channel. In channel only we'll be getting errors. So where do we find error? We'll be finding the errors only at your receiver side, which is being added due to the noises or channel conditions. So we need to perform this syndrome decoding only at your receiver's decoding part. So there, if you perform YH transpose, there perform YH transpose, easily we can identify the bits which is being errored. How do you identify that? If there is a non-zero element. If non-zero element is there, error in that code, error in that code vector. When we do YH transpose, if any elements for that corresponding code vector we get as a zero, sorry, non-zero, if we get a non-zero, then it is an error. And how to rectify that error, we'll see that also in detail, no issues. We are having still a lot. If YH transpose is 0, no error. No error will be present in that code vector. Okay. Any other questions or doubts? If no error, we can easily validate it. No issues. If there is an error, we have to perform some error controlling. We'll see that also in next class. Kindly await, I'll take the attendance. Okay, let me see. Wait for another 5 minutes, I'll take the attendance. Yeah, K Vamsi is present. K Vamsi. Yeah, Pawan Kalyan Reddy. Still, he didn't join the class. Both the Vamsis are absent.
Sir, A section only absent, sir.
I got only one news. Yes,
A
Vamsi.
section Vamsi, he informed you, no, sir.
Tell me, Lakshman.
Yesterday night.
Okay. That is A section Vamsi.
Yeah, sir. Roll number 9, sir.
Vamsi. Okay. So K Vamsi absent. Pavan Kalyan Reddy absent. Sri Vishnu is there. Sri Vishnu. Is Sri Vishnu present? No, Sri Vishnu is absent. Okay. Sri Vishnu is absent. So absentees are A section Vamsi, C section Vamsi, Reddy Kumar, and Vishnu. And Pavan Kalyan Reddy. So 5 members are absent. Remaining all are present. Okay. Thank you. You can leave the meeting.